All right, today we are going to take a look at covalent bonding. So you should have this sheet with you, and you're going to be filling out, adding some notes along as we read through it, and we'll do some examples at the bottom. Okay, so covalent bonding occurs when pairs of electrons are shared by atoms. So we're using pairs of electrons, so 2 electrons at a time. Since electrons are being shared by atoms, they do not form ions or have charges. We're not exchanging, we're not getting positives and negatives anymore. Atoms will covalently bond with other atoms in order to gain more stability, which is gained by forming a full electron shell, right? Getting that octet that we've discussed before. By sharing their outermost or valence electrons, atoms can fill their outer electron shell and gain stability. Nonmetals will readily form covalent bonds. So we're going to deal with just nonmetals now. We did metals and metallic. We did the mix of both in ionic. Now we're dealing with just nonmetals. So nonmetals will readily form covalent bonds with other nonmetals in order to obtain stability, and can form anywhere between 1 to 3 covalent bonds with other nonmetals, depending on how many valence electrons they possess. Although it is said that atoms share electrons when they form covalent bonds, they do not usually share the electrons equally. So that's something that we'll be looking at as we go through the unit. A single bond is when 2 electrons or one pair of electrons are shared between 2 atoms. Okay? It is depicted by a single line between 2 atoms. Although this form of bond is weaker and has smaller density than a double bond and a triple bond, which we'll look at soon, it is the most stable because it has lower level of reactivity, meaning less vulnerability in losing electrons to atoms who want to steal them. So to see a single bond, a good example is hydrogen, H2. So a normal hydrogen atom has just 1 valence electron each. So if they bonded together, they're going to share those 2 electrons to form a single bond. And this is how we would represent it. The 2 hydrogens with that line between it, and that line represents 2 electrons. Okay? Now, a double bond is when 2 atoms share 2 pairs of electrons with each other. It is depicted by 2 horizontal lines between 2 atoms in a molecule. Okay, so 2 horizontal lines. This type of bond is much stronger than a single bond, but less stable. This is due to the greater amount of reactivity compared to a single bond. So let's take a look at an example of that. O2, or oxygen. If we looked at its dot structure, and I'm going to put the dots in kind of a strategic spot to make this easier to see. We know we've got 4 and then 2 paired ones to get their 6 valence electrons. Again, if we looked at these 2 being shared and these 2 being shared, we could form 2 bonds. So if we look at the structure, oxygen's going to get that double bond between it, and then it will have 2 lone pairs of electrons on each. And I just spread them out. They can go kind of anywhere on the atom. The only place that the lone pairs, what we call these, cannot go is where the bonds already are. Okay, we can't put the lone pairs right here because there's already a bond there. So this is a double bond. So each of these lines represents 2 electrons. So we've got 2, 4, 6, 8 for that oxygen, and 2, 4, 6, 8 for that oxygen. The shared electrons count for both atoms. Okay, so each one has its octet. All right. Now, a triple bond is when 3 pairs of electrons are shared, as you might suspect, between 2 atoms. It is the least stable of the 3 general types of covalent bonds and is very vulnerable to electron thieves. All right, but it's also hard to break these bonds. So nitrogen, which you saw in our video yesterday. So if we looked at the structure of nitrogen, it has 5 valence electrons. I'm going to put its pair on the sides so we can see this a little easier. So nitrogen will share those 2 electrons, and share those 2 electrons, and share those 2 electrons. So what we form is a nitrogen triple bonded to another nitrogen, and then we get 2 lone pairs of electrons. So if we look at one nitrogen, we can say it has 2, 4, 6, 8 electrons, and this nitrogen has 2, 4, 6, 8 electrons. They both have their octet. Now, Drawing simple, what we call diatomic molecules, and we'll talk more about those in a second, are pretty basic. We can figure out how to draw them. But when we get into more complex structures, when we have more than one type of element and some more than just two atoms, we need a method for drawing them, okay? And that's really what this second part is all about, and what we're going to be learning today is how do we draw these properly and have a method so that it works every time and you're not just stumbling around trying to put lines and dots everywhere. Makes it way easier. So on a little side note, we've got 3 molecules here that are all made of the same element. So there are actually 7 elements that can occur in nature in pairs if they're not bonded to another atom, to other elements. So if they're bonded to other elements, we can have just one of these. But if they're by themselves in nature, they come as pairs. So we call these diatomic molecules, di meaning 2, atomic meaning atoms, and so they create a molecule of the same atom. So the 7 elements are hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. The easiest way to remember these is a really dumb word, but it works. I called them the Hofbrinkel elements. All right, so hydrogen, oxygen, fluorine, Hof, bromine, iodine, nitrogen, and chlorine, so Brinkel. All right. If you also look on the periodic table, the way they are set up, you've got nitrogen, this is tiny, oxygen, fluorine, chlorine, bromine, and iodine. It makes something that looks like a 7 in that corner, but that's only 6 of the elements. There's one more, and the other one is hydrogen on the other side of the periodic table. So we've got those 7 elements. They form diatomic molecules. Now, you do need to know these, okay? So that's a little thing to star. Know these. All right, we need to know who our diatomic elements are. It's important. Okay, now what we're going to take a look at, slide this underneath, is how are we drawing these dot structures, okay? What are our steps to do these? Now, the key to this is that we are going to follow these steps in order, okay? They have to be done in order. If you skip around, your structure is going to be messed up, okay? So that's the biggest thing, is follow the steps, follow them in order. When you get to the steps that are done, you don't have to necessarily do all the steps for every molecule, but some of them you will need to do all the steps. So we'll see how that works. All right, we're going to start with a basic diatomic molecule, one that we saw like up at the top. We're going to do Cl2 chlorine. So the first step is to find the total number of valence electrons for the compound by adding up the number of valence electrons for each atom, or given by each atom. And then if we deal with polyatomic ions, we probably won't so much in this class, but if you ever see one, the charge will tell us how much to add or remove from that total. So chlorine has 7 valence electrons each, and we have 2 of them, so we have 14 electrons to use, okay? Now, that checks off our first step there, okay? Step 2, write the symbols for the atoms. Show which atoms are attached to which, and connect them with a single bond. So we are always going to start with a single bond, okay? You're not just going to throw a double or triple in there because it sounds fun, I know. Less exciting, but so I always just lay my 2 atoms next to each other, or if it's multiple atoms like this, we're gonna just kind of lay them in a line until we get too many, and then we'll start adding them on the top and bottom, and then we're going to connect them with a single bond, one line. So that represents 2 electrons. So you can see we've still got 12 electrons to use. So now we can read through the rest of this. This talks about polyatomic ions, which doesn't apply to this. And then this is talking about the central atom. We only have 2 atoms, so neither of them are really the central atom. They're the one in the center. All right, so step 3, we're going to complete the octets around all the atoms bonded to the central atom. When there's no central atom, we want to complete the octets around what we've got, which means we want to give them, we're going to do that by adding lone pairs, okay? Lone pairs are 2 dots, okay? And they represent 2 electrons, okay? We are never using a single dot by itself, okay? okay? That will never happen, all right? Single dots cause what are called free radicals, and we don't have those at this level. So don't worry about having single dots. We need pairs. All right, so we're gonna add pairs of electrons around our chlorines until we have 8. So this chlorine on the left, I'm gonna start with it. I've got 2 already with the bond. So here's 4, 6, and 8. Okay, making sure they're on opposite sides from each other, and they're quite obviously 2 dots, okay? We don't want to have the tiniest dot in the world that we can't see. So that's 8 electrons. That means we have 6 more. We're going to do the same thing to this chlorine. So it already has 2 from the bond. Here's 4, 6, and 8. So it has its octet. So we count our total. We've got 2, 4, 6, 8, 10, 12, 14. We have used all of our electrons. So those are good. And everybody has their octet. So that's good. So those are 2 things we want to check. All electrons used, and we have an octet on all the atoms. Okay? Now, let's check the other steps. Number 4 says place any leftover electrons on the central atom. Now, we don't have any leftover electrons, so we don't need to worry about that. Okay? And then step 5 says if there are not enough electrons. So this is what we do when we have leftovers or not enough. We don't have either of those situations, so we're fine. We can move on. So let's try another one. So we've got SF2. Sulfur has 6 electrons. Each fluorine has 7. So 7 times 2 gives us 14. So we have 20 electrons total to use. Okay. Now that finds our total number of electrons. And number 2, we're going to write the symbols for the atoms to show how they're attached. Now, formulas are often written, now often, not always, okay? Be careful with those words. Written in the order in which the atoms are connected in the molecular ion. So what that means is our first element is typically going to be our central atom, and then the other ones are going to be attached to it. So I'm going to go ahead, like I said before, and lay them out in a line, and then we'll connect them with that single bond to get our layout, those single bonds. So this sulfur has 4 electrons already, and each fluorine only has 2. That takes care of step 2. We're going to move on to step 3, where we're completing the octets by adding those lone pairs. Now, we are going to do that on all the atoms bonded to the central atom. So we're going to do it on the outside atoms first. Okay, so lone pairs on outside atoms first. Okay, so that means our fluorines. So each fluorine already has 2. We're going to add those 3 lone pairs to get them up to that 8 electrons. And I'm going to do that same thing on this side. And I've got plenty of electrons here. So we can count them. I know I have 8 here, and then I have 8 here. So that's 16 electrons. We've got 4 more. 4 more to use. So we're going to go to our next step. Place any leftover electrons, we have 4 left over, on the central atom. And we're going to do that as lone pairs again. Okay, so we're going to add 2 more lone pairs to use up those electrons, and that gives sulfur 2, 4, 6, 8, gives it its octet. So we have used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We've used all 20 electrons, so we used all the electrons. Everybody has their octet, so we are good. Now, again, step 5, we haven't gotten there. It says if there are not enough electrons, we have enough electrons, so to give everybody their octet. So we can move on. This one is done. Okay, CH4. So we've got carbon that has 4 valence electrons, and hydrogens each get 1, but there's 4. So we'll have a total of 4 from hydrogens. So we have 8 electrons to use. Okay, now we're going to write out those symbols of the atoms. Again, our first atom is typically our central atom, carbon, and then we are going to add our 4 hydrogens around it. I'm going to start with a line, and then I'm going to add them on the top and the bottom. Okay, and then we're going to connect them with a single bond. Okay, now we can look at it. We've written the symbols, we've connected everything, all right? We've completed the octet, or now we're on step 3, complete the octets around the atoms bonded to the central atom. Now, we only had 8 electrons, and we've used all 8 electrons. So it says, remember that hydrogen atoms only have a single pair of electrons, one bond. So that's the key here. Hydrogen gets one bond, no lone pairs. Okay, no lone pairs for those hydrogens. That's all they get. They get a line. Okay, so these hydrogens are all done. They have the max they want. Carbon has 8 electrons around it, 4 pairs. So they're done. So this has used all the electrons, completed the octets. We're happy. This one's done. All right, last one. Let's check out this one. This is where we get to finally do step 5, okay? I know, step 5 is rare, okay? You should not have a lot of double and triple bonds. They aren't that as, because they're more unstable, they're not as common, okay? So we've got 4 from carbon, 4 valence electrons, and 6 from each of our sulfurs. So we've got 16 electrons to use. So that's step 1. Step 2, we're going to write those symbols. Again, our first one is typically our central atom, and then we're going to put our other 2 on the sides and connect them with a single bond. That takes care of step 2. We're going to now complete the octets, again, on the outside atoms only to start. 2, 4, 6. They have that bond, which gives them 8. So now if we look, we've used 8, 16. We've used all of our electrons. Now what's wrong? What's wrong is that our carbon doesn't have its octet. So we've used all of our electrons, but we haven't gotten our octet. We haven't completed that other key step to finishing. So we don't have any leftover electrons, so we can skip step 4. Let's check out step 5. If there are not enough electrons to give the central atom an octet, I don't know why it says an octet, try multiple bonds. Use one or more pairs of unshared pair, or one or more of the unshared pairs, so those are our lone pairs that are not being shared, on the atoms bonded to the central atom to form double or triple bonds. So what does that look like? Okay, well, I can take this pair from sulfur and I can shift it, because it's still, if I move it to a bond, it still belongs to sulfur, but now it also belongs to carbon. And if I do that on both sides, we are gonna be able to get our octet. So we're doing this because carbon doesn't have an octet. So we move electron pairs to share. All right. So what does it end up looking like? I'm going to shift it up here because I'm running out of space. So we're going to have our central carbon. We're going to have those double bonds to the sulfur. And those sulfurs still have 2 lone pairs to give them their octet. So that would be our final structure there. So we get double bonded carbon, which has 2, 4, 6, 8. And then our sulfurs that have 2, 4, 6, 8, 2, 4, 6, 8. All right. So now, in your practice that you get in class, it has a whole table. Let me grab one. And it's on 2 pages. Now, you're not doing the entire table right now because we haven't learned the whole thing. We're going to keep revisiting this. What you can do right now is just column 1 for both pages, all right? So you're going to be given your structure. You want to first find your total number of valence electrons and then start working out. Do this in pencil. Please use pencil, because you're going to need to erase, all right? And we're going to be going over those and making sure all our structures are correct before we go into the other things, because if our structures are wrong, our analysis will be wrong, all right? All right, thank you guys. Have a great day.